Hello everyone. This is a video lecture for College Algebra Math 1314 Section 4.5 Applications. So, lots of word problems basically. The first one says compare. We're comparing these different population models of different countries here, and they say which is the highest growth rate. And so we're obviously going to be looking at the growth rate part up here. If you want a formula, I guess, it's A equals A naught E to the KT. They're going to use that throughout the section. But again, we've seen this before in one of the first sections. It's the PERT formula. Your rate is this K now. So they'll say K equals, and they just mean a rate in this particular case. So they want the rate. It's the thing up at the top, power thing. When we're looking at our rates, we got this one, this one, this one, and this one. Which one's the biggest? Oh yeah, 28 is bigger than all these other guys. So, which has the highest growth rate? Country D, because obviously it's D there. And then what is that actual number? And so that's a 2.8% growth rate. It depends on what they're wanting. If they say K equals, which sometimes they will do, you just put that answer in immediately. If they say what's the percentage, you can move it over 2 times. Either way is fine, honestly. All right, next question. It says, we have this population growth model. When will it be 916 million? This is just like the last section we did. And so there's nothing new here. What we're going to do is take this 916 and put it in, and then we're going to solve for t. And so 91613.8 e to the 0.016 t. This is a divide, ln, divide kind of problem. So I'm going to divide, put the wrong decimal place. I did it again. It's very easy to mess all this stuff up. A third time. If I'm messing up, it's very possible for you to mess up as well. So watch out for your decimals. ln both sides. I'm doing this so that I can cancel. Again, retain all of your numbers until the end. Divide once again. So I feel like we've done this before. I feel like we've done this a lot, and you're going to keep doing it a lot in this section. And so this should be very, very familiar to you. This should be just like you can talk to somebody like I'm talking to you while just doing the math, because it's just that common. It's just that familiar. We've done this before. You'll do it again. Divide, ln divide. And so I've got 25.0217. This is in years. And, you know, I forgot to write down what it had. So it would be, let's just say T is years after 2000. I'm just making something up. I can't remember what that problem was. And so then we would have the 2000 plus the 25 to make 2025 as my final answer. Okay? Cool. Another one. It says the population in 2006 is this much. They give us a growth rate, and so what's the projected population in 2045? Well, first off, how much time is going on between these two guys? And so I'm going to say the 45 minus the 6 is 39, and so my t is 39. I have my rate, that's my power, and then I have my initial population. You can call it P, you can call it A naught, whatever you want to call it. It's your initial. And so A equals A naught E to the KT, or the PERT formula, which we've done before. Both of these are fine. And so then we got the 100.7 E to the 0.0051 times 39. And you put that all in the calculator. Again, watch out for your powers. Make sure that they're all staying in the power. I feel like this section is a whole bunch of like review, basically. I know it's a word problems, and it looks different, but honestly, the math is not different. There's really no new things going on. So this is like in millions, I guess. million. All right, there we go. Cool. Let's keep on cruising. Number 4. It says population in 2007 is this much. It's projected that we're going to have this much in 2039. What's the growth rate? So again, how much time are we talking here? I think it's 32 this time. But notice that they're wanting to solve for k. And so this is my final amount, my a, and this is my a naught. Again, my initial population, or p, or whatever you want to call it. So 10.7 is equal to 39.7 e to the k. I don't really know what k is, but I know time is 32. And then I solve for k. You know what's interesting before we keep going is that my final answer is smaller than my initial population. So what we're actually doing is not a growth, it's a decay rate. So we're going down over time. And this is fine. It's just, it might say growth, and then you'll have like a negative growth. Well, that means decay. So divide, ln divide. I'm going to halfway skip steps here because it's the same thing. I'm not really skipping steps. I'm just writing it all together for you here. Divide by the 32 to the other side. And so your k is equal to ln of the 10.7 over 39.7 all over 32. Calculator. And I got negative 0.040972. And I don't know how many decimal places they're wanting, but 6 is safe. That's just my own kind of thing. I don't know if that's a real thing or not, but I say it 6 is safe. So 6 decimals should be safe enough that you can round it to whatever else they're going to need. They might just want 6, and so you're done. They might want 4, and then you can round it. 6 is a good number. Okay. So now we're talking about half-life, and they say we need to find the rate given a half-life. Well, let's talk about what half-life is first. Say that we have some, I don't know, some ball of matter or some kind of stuff. I don't know, uranium, that's a good one. So we got 100% of uranium, and over time it will decay to be 50% of what it used to be. And then it will decay again and only be 25%. And then it'll decay again and be 12.5%. Well, each time that it decays to half over time, that is a half-life. That's how that distance. So they're saying that uranium takes thousands of years, but here they say this particular substance is 14.2 days. And so I don't know what that substance would be, but we got 14.2 days, and it should be cut in half every 14.2 days. So then again, way out here would actually be 14 plus another 14 would be 28 days to get out here to this one. 14 and 14 makes 28 there, etc. So that's good to know, but how do we go and find all this? Well, we really do need to go back to the original formula, e to the kt. And then we can start plugging stuff in, and your final amount is half of what you started with. Your initial amount was 100% of what you started with. And the k they don't know, but the time was the 14.2. When you do the math, though, you actually end up with a formula, and I'm going to go ahead and show you that formula. So whenever you talk about half-life, you got this formula here: is k is your rate is equal to ln of 0.5 divided by the half-life that they told you. And so in this particular case, that would be ln of 0.5 divided by the 14.2. So why are we doing ln of 0.5? Why is 0.5 special? And the answer is yes, 0.5 represents half, because it's a half-life. And so that's what it is. I put this in the calculator, and I got negative 0.048818. Okay, that's good enough. Round it, whatever you need to do. So there you go. And half-life should always be decaying, so it's going to be a negative value right there. So again, you could do it the long way every time, but I really recommend you start using formulas here. So formulas are way better. Okay, here's another half-life problem. It says half-life is 25 years. How long until there's only 89% that remains? Well, I'm going to do two formulas now. So my K, my rate is ln of the 0.5 divided by the half-life that they give us. So that's good. We just found that one. The other one is t, which is your time. Time is going to be ln of some kind of a percentage that they give you, and you can see it's right there. And then we're going to divide it by the k that we just found, that rate. And so it's a two-step process, but this will work just as easy. So ln of 0.5, and I'm going to divide it by, my half-life is 25. So I go and find this in the calculator. So ln 0.5 divided by 25. I got a negative 0.02772588, and that's good enough. Okay, so we got that. And now I'm going to now do my ln percentage, so 0.89. You got to put it in percentage form, decimal form, I guess you could say, divided by the k that I just found. And this is why I don't round, because, well, you need to have all those in there to make it work. You could also divide it by answer. A lot of things, even Desmo Scientific uses like ANS or answer, and that would definitely speed up this process a lot. That's what I just did on my calculator. And so this is in years. Again, how many decimal places they want, it's up to the homework program, 1 or 2 or whatever, but there you go. Cool. So, like, seriously, these formulas, like, write them down. Super important formulas to use with half-life in particular, and there will be quite a few half-life problems. Okay. So this is an interesting problem here. And they're talking about the flu or something, and I've been traumatized by that, so we're not going to go through that there. But let's talk about how to get this problem working. It's called logistic growth. Hold on. Logistic. Yeah, I think that's it's logistic growth. I'm a math guy, okay? So logistic growth model. What's going on is there's a horizontal asymptote that it will eventually approach. But at first, what's going on, and this is why it's kind of an interesting problem, is that at first it looks like exponential growth for a while, but then at some point it starts to slow down, and then it starts to cap off. There's a limiting factor. So it's I would say a little bit more real world, because there's only so much of resources, there's only so much of population, there's only so much of this and that. This is the real world situation. We still get our exponential growth that we're used to, but in the end, it makes a lot more sense. Anyways, so this is a cool model. It's a cool math problem. So it says, how many initially are we talking about? Well, initially means t equals 0. And so what you do is you take that t and you plug in a 0 into your calculator and you get a number. Now, this is a lot going on, and e to the 0 is basically just a 1, so you can get rid of that. I'm going to not do that because I'm going to use it later, but I'm not going to cross through it there. But on my calculator, I am only going to be typing. I'm going to tell you it's the 107000, then 1 plus the 5300, and that's it. This is basically just times 1 right there. You don't have to say the times 1, obviously. And so what we get is 20.1848. They're saying people, so you round appropriately, just say 20 people. Okay. How many after 4 weeks? So now, again, t equals 4. Pretty simple here. I'm just going to plug all that into my calculator, and I'll show you what I'm going to say because, well, I mean, you should be able to see it anyways. But there you go. You plug a 4 in. And it takes a minute or two to type all in here. -4 in the top there. Oops, I need a E. Okay. Okay, hold on. My calculator's being a little weird. There we go. Okay. I got 1091.02. And so 1091 would be the appropriate response. And then it says limiting size. What's that cap? What's the max? How can it get higher? It's actually the numerator. And so that's whatever you have in the numerator, you put in like that, and you're done. Okay? Cool. So the math problem's pretty cool, although I don't like the topic they're talking about there, but that's okay. Moving on. So this is actually the last question I have, and it's the same logistic growth model. And so what they're saying here is X is years after 1949, and we're talking about 2007. And so I want to see how many years are we talking there. I think it's like 58 or something, but I'm going to just verify, because again, you don't want to get stuff wrong. 58 is indeed correct. So X is equal to 58. And what I'm going to do is take that 58 and plug it in right there and get an answer. And so let me do that. I don't even want to rewrite it because it's just me typing it in my little calculator here. I really recommend using Desmos. I've said it many times. I'm going to keep saying it. Use Desmos. That way you can see what you're doing. You can edit things. You can change stuff. As far as the power is concerned, you're probably going to want to use some parentheses for this guy. But in the end, it's still by far the best. Just make sure I got that. And I'm only not using Desmos because, well, I'm using my computer to record this. So there we go. So this is my answer. It's a population. I think they're talking about world population on this one or something, which is, again, pretty cool math problems. I think there's really fun topics here. Well, for this one, the other topic was kind of weird, but this one's good. So we got that as my answer. I guess you can kind of call it part A in a way. It's not really part A on this homework program, but for us, let's just say it's part A. So part B for us is that they want to compare it to the 6.4. And what they have on the homework program is like a lot of numbers and stuff. And then they have 2007, 6.4. And so like that's the one we're looking at. And so I want to say, hey, compare with 6.4. And if I subtract them, let's just say, I'm just doing this in my calculator. And I got 0.1361. And that's cool, right? And so mine was over. So mine's overestimating. And you would just click the over button. That's all. Cool. Now, there are other questions in this homework that I did not cover. Again, I'm not supposed to cover every single one of them. It's kind of like a self-discovery, I guess, for you. I tried to do all the hard ones, or at least ones that are relevant. If I didn't do one, it might not be that hard. Maybe there's something easy, or it's very similar to something I already did. Okay? But that's all I got. Thank you very much. Have a great day.